There are a couple other ways that you can solve solubility problems. They're not all going to look exactly the same as this one where we were asked to calculate the molar solubility of PbF2. So let's look at a couple other examples of solubility calculations. The next one that I want to show you is what is the solubility of aluminum hydroxide, AlOH3. And for this guy, KSP is 1.8 times 10 to the minus 33. So this one is very similar to the last one that we did, but we're being asked for solubility instead of molar solubility. Our first goal is always going to be writing out a chemical reaction, which is going to get us ready for making an ice table. Al3 plus aqueous plus 3OH minus aqueous. The initial amount of aluminum hydroxide, we have no idea. We do know that we're not starting with any ions at all. We know that we are going to be reacting X amount of aluminum hydroxide, which means that we are making X aluminum and 3X hydroxide. And let's take a look at those coefficients. AlOH3 means that you're making 3 hydroxides, which means that your change down here is 3X. When this is all said and done, we don't know how much solid aluminum we have. We have X aluminum hydroxide and we have 3X hydroxide. The question is asking us, what is the solubility? How much aluminum hydroxide dissolves? So we just need to solve for any X and we'll have the answer to this question. We need to write an equilibrium expression, KSP, which is going to be aluminum 3 plus times hydroxide cubed. KSP is 1.8 times 10 to the minus 33. Aluminum ion is X and hydroxide ion is 3X, and that needs to be cubed. That 3 gives us that 3 right there. So this is going to be 1.8 times 10 to the minus 33, which is equal to 27x to the 4th. And if we solve for x here, we get, I believe, 2.86 times 10 to the minus 9. Remember, the units of our ice table are moles per liter. I'm going to double check my math there. 1.8 times 10 to the minus 33 divided by 27 to the cube root. I got a slightly different number on my calculator, but the magnitude is the same. It rounds to 2.9 times 10 to the minus 9. So we'll go with this. So this is the, like I said, this is the molar solubility, because ice table is going to spit out an answer to us with units of moles. And so what we need to do is convert moles per liter into the units of solubility, which are grams per liter. And we do that with just a simple mole to gram conversion. This 2.86 number is specifically the moles of aluminum hydroxide, AlOH3. We're going to keep that in mind as we do our unit conversion here. We want to get rid of the units of moles aluminum hydroxide, so we want them down on the bottom, and we want to convert into units of grams aluminum hydroxide, so we want those ones up on top. And this is going to give us 2.2 times 10 to the minus 7 in units of grams per liter, which are the units of solubility. Again, this is how many grams per liter of aluminum hydroxide will dissolve in water. Now, the last type of question that you could possibly see, the last type of question that I want to show you, is calculating the KSP from concentration data. What is the KSP of iron hydroxide, iron 3 hydroxide, if a saturated solution has hydroxide concentration that is equal to 1.35 times 10 to the minus 9 molar. What is the KSP? So this problem actually looks really different from the last two that we've done. But even though it looks quite a bit different, we're going to see that the strategy we take is almost exactly the same. We need to make an ice table, which means that we have to start by writing a balanced equation. And that's going to be Fe3 plus and 3OH minus. And where are those 3's coming from? FeOH3 means that you have 3 OH minus. Make our ice table. We don't know or care about iron hydroxide. We know that we do not start with either one of our ions. Our change will be plus X and plus 3X. And at equilibrium, we're going to have X and 3X. And so there's our ice table set up. Now this problem tells us when the solution is saturated, and that means when the solution is saturated, that means that it is in equilibrium. So when the solution is saturated, when it is in equilibrium, here's the hydroxide concentration. So that means that, maybe not and, that means that the hydroxide concentration, which we have already expressed as 3x, we know numerically the hydroxide ion concentration down here is 1.35 times 10 to the minus 9. So we know that hydroxide ion concentration is expressed as 3x, and we also know that the hydroxide ion concentration is 1.35 times 10 to the minus 9. Those are two different ways of expressing the same thing. They are equivalent to each other, which means that we can use this to solve for the value of x. X is 4.5 times 10 to the minus 10. Let's see what that does for us when we're putting together our equilibrium expression KSP. KSP is Fe3 plus times OH minus. Don't forget to cube it. What is Fe3 plus? Fe3 plus is X from the ice table. And what about OH minus? It's 3X. Don't forget to cube it. What is X? X is 4.5 times 10 to the minus 10. What about 3X? 3X is 1.35 times 10 to the minus 10. And don't forget to cube it. Don't forget that, don't forget that. And so now we should be able to calculate this KSP. And it looks like it's going to be a really small number. I'm going to start with the 1.35 times 10 to the minus 9 cubed times 4.5 times 10 to the minus 10. 1.1 times 10 to the minus 36. And that is our KSP.